In this video, we will review equilibrium and electrochemistry fundamental topics, and it's really important that we get these down because it'll set us up for success in later units such as acids and bases, and especially in thermodynamics. So, you may be used to classifying a reaction as endothermic or exothermic in terms of if energy was gained or lost. But endothermic and exothermic are specifically referring to if heat is gained or lost, and energy is not only measured in heat. So what has been developed is the Gibbs free energy, and that stands for delta G, and the little not sign that I've just highlighted in red, that means at standard conditions. And this is the total energy of a system that is gained or lost. So if it's negative, you lose energy, and if it's positive, energy has been gained. And what is important to understand is that it is very favorable to lose energy. Okay, it's kind of like money. It's not difficult to spend money or to lose money, but it is difficult to gain money. Okay, so a favorable process loses energy. We just talked about that, and thus it's going to have a negative delta G. And that's going to be referred to as spontaneous, and we will commonly write spontaneous as spon. And then a non-favorable process is going to gain energy, and that's going to have a positive delta G, and that's going to be non-spontaneous. And on the AP Chemistry test in May, they no longer use the terms spontaneous or non-spontaneous. However, you can use those terms. What you'll typically see is more fancy language, and spontaneous will be called thermodynamically favorable, and non-spon will be thermodynamically unfavorable. Okay, so that's just kind of some vocab. On our formula sheet, we have these three delta G equations, and the first one we haven't talked about yet. We'll see that in thermodynamics, and it's kind of frustrating that I wish AP would just call them all delta G, because they are. So just know that. And we're going to go through kind of when you would use these, but we want to think about delta G kind of like a middle value that in some problems we'll have to travel through delta G to get to where we want to go. So I am going to scroll down to some practice problems, and let's look at one. We've got a redox reaction, and we need to determine the equilibrium constant K. Before I even think about that, I'm going to kind of make note of what's important. We're given the voltage, and it is a positive voltage. So that means that it's spontaneous, and when something is spontaneous or thermodynamically favorable, here's what I know about it, is I know that the voltage will be positive. I know that it's favorable to lose energy, so delta G will be negative. And I know that it's going to be product favored because it's spontaneous and it's forming those products that I just circled. And that means that K is going to be greater than 1 because K is equal to products divided by reactants. And if it's product favored, that numerator will be very large in comparison to the denominator. So if I want K, I'm going to go back and look at my formula sheet. K is right there. And so I need to find delta G most likely to get there, but I'm only given the voltage. Well, if I look at the second delta G equation, voltage is in that one, so I'll first do that bottom equation, this one right there. Okay, so let's go ahead and do that. As always, if you're using a formula, you should write it out. That way your grader will just know exactly what you're doing. Minus NFE. And then what I can plug in is N represents the number of electrons that are transferred in this process. And what I need to do is I need to have this balanced. And so let me just double check here really quickly. Yep, I have balanced it this way. And that's a longer process that I'm not going to discuss in this video. But what that means is that the number of electrons transferred is 2. Faraday's constant is 96,485 coulombs per mole of electrons. And then the voltage is given 0.67 volts. And when I solve for delta G, it's going to be negative 1.29 times 10 to the 5th joules per mole. And it is very common for a delta G value to be very large, like we see here, in terms of its times 10 to the 5th. And it's negative, which is what we anticipated because we had a positive voltage. Now I can use the second delta G equation. Delta G is equal to minus RT ln of K, and delta G is minus 1.29 times 10 to the 5th joules per mole. You need to know that delta G has units of joules per mole. Sometimes AP, they'll ask you to convert it to kilojoules, and that's fine, but when you do your math, it'll always be joules per mole. R here is 8.314, and if you're ever in doubt of which R to use, the R 0.0821 atmospheres times liters divided by moles times Kelvin is only used for gas laws. And hopefully you can recognize that this is not a gas laws problem, so we don't need to use that. We are given the temperature at 298 Kelvin. And then we're solving for K, and so we have natural log of K. When you are given natural log, and the variable is within the natural log, what I want you to do is I want you to isolate the natural log of K, so we'll divide each side by 8.314 times 298, and so I've done that, and ln of K equals 52.18. And so to get rid of K, what we do is we take E to whatever this number is, and on this problem that is 52.18, and that will equal K. Oftentimes in your calculator this might give you an overflow error, so if that happens then you leave your answer like this and you won't get counted off any points. But if your calculator does solve it out, and mine does here, I get 4.61 times 10 to the 22nd, and that equals K. And that is exactly what I anticipated because I already said it was product favored, and that is a very large K, K greater than 1. Okay, let's look at a second example problem. On this one, we're looking at what happens if we multiply and divide reactions. What happens to K? So the first thing I want to do here is I want to write my equilibrium constant expression. And remember, the only thing that gets put in your equilibrium constant expression are aqueous things or gas things. Solids and liquids are not included. So I'm going to take PB plus 2 to the first power times H2 molarity to the first power divided by H plus hydrogen ion to the second power, and then lead is left out. The reason why solids and liquids are excluded from your equilibrium constant expression is because their concentrations do not change for solids and liquids. Okay, so this is like our last example. I've given you the voltage and I want the equilibrium constant. So we're going to do delta G equals minus NFE. Delta G is kind of our middle value to get to K. Lead goes from 0 oxidation state to plus 2, so that is 2 electrons that get transferred. Faraday's constant is 96,485 coulombs per moles of electrons. And then the voltage is given at 0.13 volts. When I plug this into my calculator, delta G, I am anticipating that it'll be negative. That's because it's spontaneous, and so it must be losing energy, because that is a favorable thing to have happen. And I get negative 2.5 times 10 to the fourth joules per mole. Now I can use my other delta G equation. Delta G equals minus RT ln of K. And delta G is negative 2.5 times 10 to the fourth joules per mole. That equals minus R. R is 8.314 joules divided by moles times Kelvin, because this is not gas laws. I believe on this problem, I did not tell you what the temperature is, and I'm looking to see if I did, but let's assume it's just at 298 Kelvin, 25 degrees Celsius, then times the natural log of K. I will isolate the natural log of K by dividing over 8.314 and 298. And when I do that, I get 10.091. So I'll take e to the 10.091 power equals K. And let me plug that in. And I get K is equal to 2.41 times 10 to the fourth. And we're going to use this number for the rest of this problem. So what I'm asked in part C is to solve for K for the reverse reaction. So if my reaction was products divided by reactants in terms of how I solve for K, when I have the reverse reaction, my reactants will become my products, and my products will become my reactants. And so basically, what I'll want to do is just take the reciprocal. So I'll have 1 divided by K, just flip it. So I'll have 1 divided by 2.41 times 10 to the fourth. When I math that out, I will get 4.15 times 10 to the minus 5. And that should make sense, because if I'm product favored in one direction, and that would be spontaneous, I am going to be non-spon or non-spontaneous in the reverse direction. Okay, let's look at part D. On this, I believe, and I'll have to scroll up here, what I've done is my coefficients have been doubled. We need to remember that our coefficients go in the exponent location. So what I'll do is I'll move this down here. And what I know now is that my Pb plus 2 is now to the second power, my hydrogen is to the second power, and my hydrogen ion is to the fourth power. So basically what I have done is I've just squared everything. So if I double my coefficients, I'm going to double my exponent of K. And so I'm going to take my original K, which is 2.41 times 10 to the fourth, and I'm going to square it. And I can do a little bit of mental math here, and I can say 2.41 squared is going to be something a little bit over 4, maybe a little bit closer to 5, and then 10 to the fourth squared would be 10 to the 8th. And the reason I'm telling you that is for like multiple choice where you may not have a calculator. But if I plug this in, I get 5.81 times 10 to the 8th. On this next problem, what has happened is from the original reaction, I have divided my coefficients by 2. So what that means is my exponents will be 1/2, 1/2, and then just 1. So my K will be to the 1/2 power. So I'll take 2.41 times 10 to the 4th to the 1/2 power. I don't know the square root of 2 off the top of my head, but I know it's going to be 1 point something. And in fact, 2.41, the square root of that is 1.55. And then the square root or half of 10 to the 4th would be 10 to the 2nd. And so I get 10 to the 2nd. And so that would be that answer. And then on this last one, what has happened is I have the reverse reaction and my coefficients are halved. So what that means is for the reverse reaction, I'll take the reciprocal. So I'd get something like that. So I've done the reverse reaction, but then they're halved. So I need to take k to the 1/2 power. So this is 1 divided by 2.41 times 10 to the 4th. That's my original k value, to the 1/2. And when I do that, I get 6.44 times 10 to the -3rd.